So we are continuing to go through the OCaml.org documentation pages. So we have been going through the data structure section um, under learn language. We finished options and arrays. So before going to maps and sets, which requires completing functors, I thought we will do the sequences section. So let me paste the link in the chat. But feel free to ask any questions you have as we go along. All right. So let's begin going through this section here. I have pushed the notes as well for this session in the GitHub repo. I'll share the link at the end of this session. Right. So sequences are very much like lists. They may be infinite. Okay. So examples of sequences could be incoming requests from a server, or it could be readings from an embedded sensor, or even system logs. Okay. So all of them have unforeseeable termination, and it is easy to consider them as potentially infinite. So the sequence elements are computed and on demand and not stored in memory. Okay. They allow for reducing the memory consumption from a linear to a constant space. So let's look at example of a type sequence.t. So this is a list, but when it is not empty, its tail is basically frozen. So we'll understand this a bit more with examples. So let's consider the definition of sequence.node. It's either nil, right, or it is a pair. Now it's a mutually recursive definition, and it's very similar to list definition, where a list either can be empty or it can be a list here, right? So the whole point of this definition of sequence.cons with a capital C is that it is a function returning a sequence, while in the case of a list, it is just returns a list, okay, of this type. So a more detailed comparison is given here. So for both the constructors of list and sequence.node, so we have, in the case of empty list and sequences, they define the same way. We have constructors without any parameters, sequence.nil and empty list. In the case of non-empty lists and sequences, both are pairs, right? And in the case of a list, the second member is a list, while in sequence it returns a function which returns a sequence.node. Okay. So what this definition here says is the value of type sequence.t is frozen because the data it contains is not immediately available to us. Okay. So a unit value is supplied to recover it, and which is basically called unfreezing it. But remember that unfreezing only give the next immediate value in the sequence, and it will still return the second argument of seq.cons as a function. So frozen by function tails explain why sequences can be potentially infinite. So until a sequence.nil value has been found in the sequence, we can't be sure if some value will be returned. So as I said, these are some examples of requests coming from a server or reading from a embedded sensor. Now, this is very similar to what you would have seen in Haskell, for example, called as a thunk. It's basically lazy evaluation. OCaml is as much of eager evaluation. It wants to compute the values as quickly as possible. So in OCaml, any value of type t, it can be turned into a constant function using this construct. So this is called a thunk. So the sequence.t values are thunks. You just return a function. Okay, so with the analogy that we used earlier, A is frozen in thunk. So here's an example of how to build infinite sequence of integers. So we have let recursive ints with an argument n, and basically it's a function with sequence dot constructor of n and ints of n plus 1. So let's try this in utop. Okay. Let recursive ints n in sequence dot t turns a function sequence dot construct n and ints of n plus 1. Okay. So the function looks like it's building an infinite sequence of n plus 1, n plus 2, n plus 3 and so on, right? But in reality the machine has bounds, so it's not indefinitely increasing. So when it reaches max int, it will come back to min int. So what is max int and min int? It's a very high number. Similarly, we have min int, which is the negative minimum value for integers. Right. Now, the OCaml standard library does have a module on sequences called SCQ. So it contains, for example, the iter function, similar to what we have seen in the list module, which is list.iter. So we can do sequence.iter print ints starting with 0. So this will basically start printing the integers forever, and this will basically keep running. So I have to press Ctrl C to break this loop. Right. So then I press Ctrl C to break this one. Now, if you want to ignore the output, the same infinite loop, we can use this sequence.iter, ignore the output in 0. It will keep running forever, but then I have to press Ctrl C to interrupt the execution. But the key thing here, the key takeaway is that it doesn't leak any memory. This runs in constant space. So even though it's running as an infinite loop, it is working in a fixed memory space. So we can actually confirm this by monitoring the space consumption of the program, and it will not crash basically. But this example here, this should allocate a list of length proportional to the running time, and hence it will run out of memory very quickly. So let's try this. Let recursive ints n and call ints again of n plus 1. So we are constructing an infinite stream here. Right now, if I call ints of 0, it will, after some time, it will throw this error saying stack overflow during evaluation. Right. Now let's look at an example on how the seek module in the OCaml standard library is defined, especially the take function. The sequence.take function returns a specified number of elements from the beginning of a sequence. So it looks something like this: recursive take number of elements in the sequence. If n is less than or equal to 0, then you return nil, sequence.nil. Otherwise, for the match sequence, you get it from the pairs. There is no match, you return nil. Okay. Now, this is a common pattern for recursive functions over sequences. So we will have a sequence called sequence, and you will have the unit value. So when executed, the function basically begins by unfreezing the sequence, and it calls sequence with the parenthesis, does the pattern matching to look inside the data, and then returns it. The key thing here is writing take 10 of sequence does not compute anything. It's only a partial application. And it just returns a function and needing a unit to actually produce the result. So we can actually use this to print integers without looping forever. So let's try this example here. So we have sequence.ins of 0, pipe it to, let's say we take 43, and do list.off sequence. Right, so you're generating this infinite inst stream, taking the first 43 elements on the sequence and converting it into a list, right, which is what we get here. Okay. The seek module also has a filter function. So this is given by seek.filters. It has a function which this function takes type A and ascertains whether it matches the filter condition, takes a sequence and returns a new sequence that matches the filter condition. So an example is given here where you want to generate a list of prime numbers. So here they are using this trial division algorithm. Which is used using the integer factorization algorithms, right? So there's a Python example here. So we just implement this in OCaml. So let's try this. Let recursive trial div sequence match sequence with if sequence dot cons of m and sequence, return sequence dot cons of m, again call trial div with sequence dot filter as n mod m is greater than 0, close sequence. Then you have the other case, sequence we say let primes is sequence dot ins2. So the link to the algorithm is given in the page, so you can try it out. yourself. So that's the definition for trial driven primes. Now we can get the first 100 prime numbers. So I can say primes sequence dot take 100 and convert that sequence to a list, and we get the list here. Right. So the function trial div is recursive in OCaml. Sometimes it's called as co-recursive. What is co-recursion? Right? Although it may not terminate, it can indefinitely produce valid output. So the definition of co-recursion is given here. So in recursion, usually you start on data further from a base case and break it down into smaller data, repeating until one reaches a base case. In co-recursion, you start from a base case and keep building it up iteratively, producing more data removed from the base case. Okay, you can go through this definition also later from the Wikipedia page. Right. So let's continue. Look at more functions. So the seek module also has higher order iterative functions, seek.iter, similar to what we have seen in array and list as well. So you have iter, map, and fold left. Now there is no fold right function, right? But you can write a unfold function is also not there, so we can implement that as well. So we say let recursive unfold fx match fx with, in the case of none we do seek.nil sum of x comma sequence seek dot x comma unfold f sequence. Okay, so that's the definition of unfold. Now seek.unfold does not have a sequence parameter but a sequence result. Unfold, it provides a means to build sequences. The result that is returned by sequence.unfold fx is the sequence built by accumulating the results of the successive calls. Okay. That is what is given here. So we can implement seek.ins using seek.unfold in a very compact manner. So we can say let ins is equal to seek.unfold sum of n and n plus 1. Okay. Now we can of course map over sequences, and that can also be implemented using seek.unfold. So here's an example of how to write this. So we can do let map f seek.unfold take the sequence seek dot unconst pipe it to option dot map function sequence apply f to x and sequence. Let's map. So let's test it out. So we can do sequence dot ins of 0, map it to x, and then sequence dot take of 10, and then we call list dot of sequence. and we get the square of each of the elements that we have seen earlier in the list. Now, the function seek.onCons returns the head and tail of the sequence if it is not empty, otherwise it just returns none. Now, let us look at a bigger example of reading a file. So, we can define this input line option, input line OPT channel, try some input line channel with end of file none. Okay. Now, I am going to read a file, cin open in, let's say I am going to read etc resolve.conf from the system in cin seek.unfold input line OPT, then I am going to pipe it to sequence iter, just print end line and then we close. Okay. So, it basically reads the etc resolve file contents here. Good. So, sequence module contains this definition here, right. So, this is the sequence with .cons with small c. Okay. Sequence.cons is a function, but sequence.cons with the capital C is a variant constructor. Okay, so you need to be very careful with the difference. So, let us illustrate this with an example here. So, let us say we want to define the Fibonacci sequence. So, we are going to do let recursive fibs mn sequence dot construct m fibs of n and n plus m. Okay. Now, this is an unending recursion which will blow away the stack. Okay. So, if I try to run this, fib starting with initial values for the sequence as 0 1, it throws stack overflow during evaluation. This is not exactly what we want. So, the definition that we should be using here is the seek.cons value constructor. So, we say let recursive fibs mn seek.cons m fibs n and n plus m. Okay. Now, we produce the Fibonacci numbers. We can call fib 0 1, call seek.take 10. This is going to produce an infinite stream, so you want to take some of it and then you convert it into a list. This is the first 10 Fibonacci numbers. So, the key difference here is in the recursive call fibs of n plus m. Right. In the first case, here we are providing all the arguments, right. In the second case, this is only a partial application, right. Since in OCaml the evaluation is eager, in the former case the recursive call is triggered and a non-terminating loop occurs. But in the case of sequence.constructor, the partial application is immediately returned as a closure. So, as we need values, you take it. So, sequences are functions. So, the functions working with sequences must be written correctly. A sequence consumer, the partially applied function parameter, and a sequence producer should have a partially applied function result. So, be conscious when you are writing these. Now, throughout the standard library, sequences are used to do conversions between multiple data types. So, we have already seen a list of sequence here. We are able to generate a stream of sequences, take some values and convert that sequence into a list. Similarly, you can convert them to arrays or to strings. Okay, similar functions are also provided for sets, maps, and hash tables. So, when you are writing a module, it is generally good to write these functions, to sequence and off sequence functions. Now, some additional libraries to handle large flow of data is given here for reference. And there used to be a stream module which was removed in 2021 with the release of 4.40, but there you should find some documentation that still exists for this. So, my suggestion is to try this in UTOP. So, I am on OCaml 5.1.1 and the examples work fine here. Right. So, please rewatch this video, try the examples. I will make this video again available on the YouTube channel. Let me share the link to the channel. I also push the notes in the GitHub repo for today's session. So, please go through that, and we'll try to finish up with the rest of the module section in the coming days.